everyone, welcome back. Today, we're going to go through a few advanced circular motion problems. And I'm going to go through these pretty quickly because I got a number of them. But as I stated in my last video, they all work the same way. And what I'm going to do for each one is really the single most important part of the process, which is identifying what is providing that force toward the center and then expanding that base equation so you can see all the variables. All right, let's get started. First up, we're going to start with the very simplest one, which is the horizontal ball on string. This is if you're rotating the ball on a table surface and the plane of the circle is parallel to the ground. Quite simply here, force toward the center. Start my force diagram. This is tension 1. From this point of view, there are no other forces. The ball is moving at a constant velocity around the circle. So force toward the center is tension 1, m vt squared over r is tension 1, solve for tension 1. Easiest one you will see. Next up, satellite orbiting the Earth. So, force diagram. What is providing this force? Well, that is force gravitational. And it's not mg, it's the big one. So I'm going to start with that. Force toward the center is force gravitational. That means m vt squared over r equals the gravitational constant times mass of the planet, mass of the satellite over r squared. Now, here's the big question here. Which mass is this? Is it the planet or is it the satellite? Well, the answer to that question is, which of the objects is actually moving in the circular path? The answer to that is the satellite. So once I put that in there, these two things cancel. And that's not the only thing that cancels if you notice. One of these radiuses cancel. So that leaves me Vt squared equals g mass of the planet over r. Side note, sometimes with these problems, they like to be a little tricky. They'll give you the radius of the planet, capital R, and they'll give you the height from the surface. In that case, the radius you use for centripetal would be radius of the planet plus h. So in that case, you could have Vt squared equals g mass of the planet over r plus h. It's possible if they give you these two things separately. From here, typical things to be asked for: what's the velocity of the satellite? Or how far from the center of the planet should be if they give you the velocity, etc. Once you get to this point, you're golden, because then you could solve for anything that's missing. Next up, car moving in a circle. We actually did one of these. What force is providing the force to keep the car on the circular path? That is force friction, and we're assuming this is a flat horizontal road. Force toward the center is force friction, which means m vt squared over r equals mu times force normal. If it's a flat road, force normal will be equal to force earth, which is mu mg. In that case, masses cancel. I have vt squared over r equals mu times g. From here, rearrange and solve for whatever you're looking for, and that is typically mu. Or they can give you mu and ask you what is the highest velocity this vehicle can move at without slipping. Next up, theme park ride. This is the one where you are in the ride, moving in a circle. The force that is keeping you in the circular path is force normal. So I'm going to start there. Force toward the center is force normal. Now, there's no relationship for force normal. However, in this case, the question doesn't really involve force normal. The question usually involves friction, because there are some rides like this that exist where they spin the ride around and then they drop the floor out. The walls are typically made out of carpet or something similar, so there's a lot of friction between you and the wall. And friction is what prevents you from sliding down the wall. So I'm going to do another force diagram, and this time I'm going to do it from the side. I would have force earth on person, which is mg. I would have force friction preventing that person from sliding, which is mu times force normal. And force normal would be provided from the wall, which is what's keeping you in the circular path. Now, I may not have an equation for force normal. However, this person is neither sliding down nor sliding up the wall, which means force friction and force earth must cancel each other. That means force friction also equals mg, and I have a relationship right here. Therefore, force normal equals mg over mu. That means I expand my relationship up here, and I get m vt squared over r equals mg over mu. And there you have it. From here, typical questions. What is mu? What's the radius of the ride? What's the tangential velocity of the ride? what's the angular velocity of the ride, what's the frequency of the ride, which is something I'll show you next video.
The one other thing I would like you to notice here is that mass cancels in this equation, and that's important for a theme park ride. If you have a theme park ride where people's different masses have different accelerations, that means during the ride, everyone would be slamming into each other, and that would be very bad.
Next up, vertical ball and string. This is an important one. So in this case, the ball and string are being swung vertically. That is, the plane of the circle is not horizontal to the ground, it is perpendicular to the ground. So in other words, this is a side view. I'm going to start with my force diagram. First, we're going to do the ball at the very top of the circle. At the very top of the circle, I have two forces on the ball. Tension 1, which is pulling this toward the center, and I have force Earth, which I'll simply label as mg. That means force toward the center is T1 plus mg, just expanded, mvt squared over r equals T1 plus mg. Now, just to let you know, 1, mass does not cancel because it is not involved in the tension. 2, a very common question here would be, what is the slowest velocity you could swing this ball at and still have it remain in the circular path? And to think about that, I want you to imagine if you were to swing this around slower and slower and slower and slower, eventually it would fall out of the circular path and just drop. Well, if you swing this around slower and slower and slower, you need less force to keep it in the circular path, which means one of these forces has to change, and it's not force Earth, because the mass of the marble is not changing. Tension 1, however, can decrease. What's the smallest tension 1 can get? The smallest tension 1 can get is 0. So if you were asked what is the slowest possible velocity, you would make tension 1 0, and then mass would cancel, and you would end up with Vt squared over r equals g. But that is a very special case. I'm just mentioning it because it's actually asked for pretty commonly. Okay, while we're here, what if this marble is at the bottom of the circle? Well, to start, you have force Earth again, which I will simply label as mg. You also have tension 1, which has to be larger now because we need a net force toward the center. And my centripetal force equation would be T1 minus mg in this case. Expanded, mvt squared over r equals T1 minus mg. You are very typically asked to find the tension in this case, and notice you would add mg to the other side, so tension would be pretty large. Side note, if you're ever asked to find the forces on a roller coaster at the top of a loop, it is the exact same situation as this one. Instead of forced tension, it is forced normal pushing on the train car. Next up, car on hill. I will have mg from force Earth. I will have force normal from the ground. Fc, therefore, is mg minus force normal, because the center of my circle is somewhere around here. Mvt squared over r equals mg. Force normal does not have its own equation, so typically in this case, you're literally asked to find force normal depending on the velocity of the car. Next up, car in valley. I have force Earth, which is mg. I have force normal, which is going to be larger than mg because the center of your circle is somewhere around here, and you need a net force toward the center of your circular path. Fc equals, in this case, force normal minus mg. Mvt squared over r equals force normal minus mg. Again, you are very commonly asked to find force normal here. Next up, the banked turn. If you're not sure what a banked turn is, do a very quick internet search. A banked turn during a race. The track is usually banked so cars can take the turn a lot quicker than usual. And that is because part of the normal force actually faces toward the center to help with that centripetal force. Now, in a first year physics course, these problems almost never have friction because that really complicates the situation. An assessment will typically want to see if you recognize what actual force points toward the center, which in my above diagram would be this way. Now, let's start with a force diagram here. Here's my car. First force, force Earth, which is mg, and force normal, which is this way. Now, a very important note here. This is not an incline. This car is neither sliding up or down the ramp, which is very important because that means that the components of force normal, well, the vertical component anyway, needs to cancel, and it's going to cancel with force Earth. So that means this component is mg. Now, it also means something else. Here's my right angle. It also means if this incline is theta degrees off the horizontal, then this arrow the force normal is 30 degrees off the vertical. So that means you know this angle. And that also means if you know mg, you can get the opposite side using trig. I'll call this force x for now. And if tangent theta is force x over mg, opposite over adjacent, that means force x is mg tangent theta. Since I broke up force normal, it is essentially gone. These two cancel. That means this is my force toward the center. That means that is my centripetal force. So mvt squared over r equals mg tangent theta. If you notice, masses cancel. So vt squared over r equals g tan theta. Very common questions here. They give you the angle, they ask you how fast the car is going, or they give you how fast the car is going and ask you what angle should the bank be. In that case, you'll be using inverse tangent at some point. Next up, ball and string, cone shape. That means the string is latched to the ceiling or something at this point at the top here, and the ball's moving in a circular path here. They typically give you or ask for this angle, and the length of the string is usually involved. Again, let's start with the force diagram. Force Earth, which is mg. We also have tension 1. And again, the center point is here, directly to the right of the sphere. So I am breaking up tension 1. Again, these two have to cancel. And if this angle is theta, this is an interior angle that is also theta, which means just like last time, this is force x. How you get it is mg tangent theta. So again, force centripetal is force x. mvt squared over r equals mg tangent theta. Masses cancel. vt squared over r equals g tangent theta. Again, the difference is instead of a component of force normal keeping in the circular path, a component of tension is keeping in the circular path. All right, those are the more common complicated examples that you will see. If you ever spot them, I recommend you come back and check out this video, and you can just fast forward to whatever example you were looking at.
That being said, the base strategy for each one was the same, and it always starts with making a force diagram and finding what is literally providing that force toward the center.
I will end this here. Have a good day. This is Mr. M signing off.